What if I told you that some of the most mind-blowing engineering marvels in human history weren't built in our modern era of steel and computers, but thousands of years ago, with nothing more than stone, ingenuity, and sheer human determination? Picture this: massive pyramids aligned perfectly with the stars, aqueducts that carried water across mountains, and temples so precisely constructed they've withstood earthquakes for millennia. These aren't just relics of the past, they're masterpieces of engineering that still leave experts scratching their heads today. How did ancient civilizations, without lasers or blueprints, or even the wheel in some cases, achieve what seems impossible even by today's standards? That's the mystery we're about to unravel. Think about the last time you struggled to assemble furniture with an instruction manual. Now imagine carving a 200-ton block of granite with copper tools and moving it hundreds of miles without trucks or cranes. Sounds unbelievable, right? Yet that's exactly what the builders of antiquity did, turning unimaginable challenges into enduring triumphs. From the secret acoustics of Greek theaters that amplified whispers to the Inca's earthquake-proof stonework, these weren't just random acts of construction. They were calculated, revolutionary feats, each one a testament to human creativity and problem-solving. And here's the wildest part: we're still uncovering their secrets, piece by piece, as if solving a puzzle left behind by the greatest minds of the ancient world. This isn't just a story about stones and mortar. It's about the audacity of people who refused to be limited by their time. What drove them? What did they know that we've forgotten? And what can their breakthroughs teach us about innovation today? As we journey from the deserts of Egypt to the jungles of Cambodia, we'll decode the hidden blueprints of history's most astonishing structures. You'll discover how ancient engineers turned physics into art, why some of their techniques remain unmatched, and how their legacy whispers to us across the centuries. So if you've ever looked at an ancient wonder and thought, how on earth did they do that? You're about to get answers. Let's dive in. Ancient engineering isn't just about old structures. It's a window into how civilizations solved problems with nothing but creativity and grit. Picture a world without calculators, cranes, or even standardized measurements. Yet somehow, ancient builders crafted monuments so precise they rival modern precision. Take the Great Pyramid of Giza, aligned to true north with a margin of error smaller than a fraction of a degree. Or consider the Roman aqueducts, some still standing after 2,000 years, delivering water with gravity alone. These weren't lucky accidents, they were the result of meticulous observation, generations of knowledge, and an almost artistic understanding of natural forces. What set ancient engineering apart was its marriage of practicality and innovation. While today's engineers rely on digital models and advanced materials, their predecessors worked with what they had: stone, wood, and sheer human effort. The Inca, for example, built Machu Picchu's terraces without mortar, yet the stones fit so tightly you can't slide a piece of paper between them. This technique, called ashlar masonry, wasn't just about aesthetics. It made the structures earthquake-resistant, a genius solution in a seismic region. Similarly, the Persians invented wind catchers, towering structures that funneled cool breezes into buildings centuries before air conditioning. These weren't just tools, they were revolutions in living. But here's what's truly fascinating. Ancient engineering often blurred the line between science and spirituality. Stonehenge's alignment with solstices wasn't just about marking time, it connected the heavens to human rituals. The Maya designed their cities as celestial maps, with temples acting as astronomical observatories. For these builders, engineering wasn't just functional, it was a dialogue with the cosmos. And that's the heart of ancient engineering, a fusion of necessity, reverence, and relentless curiosity. It reminds us that innovation isn't just about technology, it's about seeing the world differently and daring to shape it. The ancient world's greatest structures weren't just built on brute strength, they were crafted with mathematical precision that would impress even today's engineers. Take the Great Pyramid of Giza. Its base is a near-perfect square, with sides aligned to the cardinal directions with an error of just a fraction of a degree. How did they achieve such accuracy without modern tools? The answer lies in the stars. The Egyptians used the constellations, particularly the circumpolar stars, as their celestial compass, tracking their movements to pinpoint true north. This wasn't just astronomy, it was geometry in action, a marriage of math and the heavens that turned stone into a timeless wonder. Then there's the Parthenon, where the Greeks embedded the golden ratio into every column and curve. This mathematical proportion, roughly 1.618 to 1, appears in nature, from seashell spirals to the arrangement of leaves, and the Greeks believed it held the secret to beauty and balance. By designing their temples with these ratios, they created structures that felt harmonious to the human eye, as if nature itself had shaped them. But it wasn't just about aesthetics. The golden ratio also distributed weight evenly, making buildings more stable. When you walk through the ruins today, you're not just seeing art, you're witnessing math made tangible. Even more astonishing is how these principles crossed continents and cultures. In India, the Taj Mahal's symmetrical design mirrors precise geometric patterns, while the Maya calculated the dimensions of their pyramids using a base 20 numbering system, aligning them with solar and lunar cycles. These weren't coincidences. Ancient builders understood that math was the invisible framework holding their world together. They didn't have calculators, but they had observation, patience, and an unshakable belief that numbers governed everything from the rise and fall of the sun to the strength of their temples. What's truly remarkable is how these mathematical secrets were passed down. The Romans, for instance, recorded their engineering formulas in detailed manuals, ensuring that knowledge survived generations. Meanwhile, the Inca used knotted cords called quippers to encode data, proving that math wasn't just for construction, it was a language. Today, we're still deciphering their techniques, like archaeologists piecing together a grand numerical puzzle. Every time we uncover another clue, a perfectly angled wall, a precisely measured foundation, we're reminded that ancient engineers weren't just builders. They were mathematicians, philosophers, and artists, turning equations into enduring legacies. The materials used by ancient builders weren't just durable, they were revolutionary, crafted from the earth itself and refined through centuries of trial and error. Take Roman concrete, a mixture so resilient it's still intact after 2,000 years of seawater pounding against harbors like Caesarea. Modern scientists were stunned to discover its secret, volcanic ash known as pozzolana, which reacts with seawater to form crystals that actually strengthen the material over time. While our modern concrete crumbles in decades, theirs grew tougher, a testament to their mastery of chemistry long before the periodic table existed. Then there's the Inca stonework, where massive blocks of granite and andesite were shaped to interlock like a three-dimensional puzzle. Without metal tools, they used harder stones to grind and polish surfaces, achieving fits so precise the joints are virtually invisible. This wasn't just craftsmanship, it was geology in action. The Incas understood how different stones responded to pressure, selecting materials that would settle together during earthquakes, creating structures that swayed but never collapsed. Modern engineers call this kinetic architecture, But for the Inca, it was simply the wisdom of their ancestors, passed down through generations of working with the land. Even more astonishing are the forgotten recipes like the Chinese's sticky rice mortar, used to bind the Great Wall's bricks. By mixing rice paste with lime, they created a composite stronger than pure lime mortar, one that resisted weathering and even repelled pests. Similarly, the Egyptians added gypsum to their plaster to prevent cracks in the pyramid's inner chambers, a trick still used in restoration projects today. These weren't random experiments, they were deliberate innovations born from observing how materials behaved under stress, heat, and time. What's striking is how these ancient builders turned limitations into advantages. No steel, they used timber reinforcements in Hindu temples, designing flexible joints that absorbed seismic shocks. No cement, the Persians mixed clay with straw to create lightweight, insulating bricks for their desert cities. Every solution was a dialogue between human ingenuity and the natural world, a reminder that the best engineering doesn't fight nature, it collaborates with it. And perhaps that's the most enduring lesson. Their materials weren't just chosen for strength, but for harmony. When we touch these ancient walls today, we're not just feeling stone, we're touching the legacy of minds who saw the earth not as an obstacle, but as a partner. One of the most baffling puzzles of ancient engineering is how civilizations lifted and transported colossal stone blocks, some weighing as much as 1,000 tons without the machinery we take for granted today. The Egyptians didn't have cranes, the Olmecs lacked wheels, and yet both cultures maneuvered stones so massive that modern engineers still debate their methods. Take the unfinished obelisk of Aswan, a single piece of granite that would have stood 137 feet tall if completed. Just carving it from the bedrock was a feat, but how did they plan to move it? The answer might lie in something as simple as wet sand. Experiments show that dragging sledges across dampened surfaces reduces friction dramatically, making it possible for teams of workers to haul unimaginable weights with ropes and sheer manpower. But not all ancient solutions were so straightforward. In Central America, the Olmecs transported basalt boulders from quarries over 50 miles away to create their famous colossal heads, each one a towering portrait carved with eerie precision. Without beasts of burden or wheels, how did they do it? Some researchers propose they used log rollers and lever systems, while others speculate about rafts and river networks. Then there's the tantalizing, though controversial, theory of sonic levitation, where vibrations or sound frequencies might have reduced the effective weight of stones. While this sounds like science fiction, it's worth noting that many ancient cultures from Tibet to Egypt have legends of stones being moved by the voice of the gods. Could there be a kernel of truth buried in these myths? What's undeniable is that these builders understood physics in ways we're still unraveling. The Egyptians didn't just drag stones, they engineered ramps with precise inclines, like the spiral ramp hypothesized inside the Great Pyramid's construction. The Incas shaped boulders with concave bases so they could rock them into place like a pendulum, minimizing the force needed to position them. These weren't brute force operations, they were masterclasses in efficiency, turning limitations into innovations. Perhaps the most humbling realization is that we've only scratched the surface of their knowledge. When archaeologists found traces of oxalic acid on stone blocks at Puma Punku, it hinted at chemical softening techniques lost to time. Meanwhile, the precision of interlocking joints in ancient sites suggests the use of advanced measuring tools we've yet to rediscover. Every unanswered question is a reminder. These weren't primitive people stumbling in the dark. They were problem solvers on par with today's finest engineers, working with the tools and wisdom of their age. And that's what makes their achievements so extraordinary, not just what they built, but how little we still understand about the brilliance behind it. Imagine an entire city thriving in the middle of a desert with lush gardens, flowing fountains, and enough water to sustain thousands, all without a single electric pump or modern pipeline. This wasn't magic, it was the genius of ancient water management. Take Persia's Qanats, underground tunnels that tapped into mountain aquifers and transported water across arid landscapes using nothing but gravity. These weren't just ditches, they were meticulously engineered channels, sometimes stretching 40 miles, with vertical shafts dug every 100 feet to allow maintenance and airflow. The math behind them was stunning. Builders calculated slopes down to the millimeter, ensuring water moved steadily without eroding the tunnels. Even today, some Qanats still supply Iranian villages with water, a testament to their flawless design. Halfway across the world, the stepwells of India turned water scarcity into architectural artistry. Chand Baori, with its 3,500 symmetrical steps descending 13 stories deep, wasn't just a reservoir, it was a community hub, a cooling refuge from the heat, and a sacred space. But the real marvel was in the details. The steps created maximum surface area, reducing evaporation in the blistering climate, while the precise depth ensured water remained accessible even during droughts. And unlike modern dams that disrupt ecosystems, these structures worked with the land, recharging groundwater and supporting local wildlife. Then there's Rome, where aqueducts like the Pont du Gard carried millions of gallons daily across valleys and mountains. The secret, a gradient so slight, just 1 foot of drop per 3,000 feet of length, that water flowed smoothly without bursting the channels. Builders even added sedimentation tanks to filter debris, a primitive but effective water treatment system. Meanwhile, in the Andes, the Inca engineered terraces with built-in drainage to prevent erosion, turning steep slopes into fertile farmland. What unites these systems isn't just ingenuity, it's sustainability. Ancient engineers didn't just exploit water, they revered it, designing systems that conserved, recycled, and distributed it equitably. In an age of climate crisis, their lessons are more relevant than ever. They remind us that the most advanced technology isn't always the newest sometimes. It's the wisdom carved into stone centuries ago, waiting for us to rediscover it. The Romans didn't just build roads, they engineered arteries of empire, crafting pathways so indestructible that after 2,000 years, their stones still lie beneath modern asphalt. Picture this, a highway system stretching over 250,000 miles, connecting London to Jerusalem, Spain to Syria, all without GPS or diesel-powered machinery. What made these roads last centuries longer than today's pothole-ridden pavement? The answer lies in their meticulous, almost obsessive approach to durability. Each road began with digging trenches 3 feet deep, then layering crushed stone, gravel, sand, and finally interlocking volcanic rock slabs, a sandwich of stability that distributed weight and shrugged off floods. But the real genius was in what you couldn't see. Roman engineers built their roads with a subtle hump called a camber, causing rainwater to drain into roadside ditches rather than erode the surface. In marshy areas, they drove oak pilings deep into the ground to create stable foundations, a technique still used in modern Venice. And their routes weren't just straight lines drawn on maps, they were strategic masterpieces. By plotting courses along ridges and high ground, the Romans avoided valleys prone to flooding, while ensuring soldiers and merchants could move swiftly without ambush. The Appian Way, one of the earliest and most famous, cut travel time between Rome and Capua from days to mere hours, revolutionizing military logistics. What's often overlooked is how these roads doubled as communication networks. Every Roman mile, roughly 4,800 feet, was marked with a stone pillar listing distances to nearby towns and the emperor who commissioned the road. Couriers on horseback could relay messages from Hadrian's Wall to the Euphrates in weeks, an ancient version of high-speed data transfer. The roads also fueled economic explosions, with wheel ruts standardized to a 4-foot 8-inch gauge, nearly identical to modern railway tracks, allowing carts from Britannia to Egypt to use the same vehicles without adjustment. Perhaps most astonishing is how these engineering principles outlasted the empire itself. Medieval kingdoms repurposed Roman roads as pilgrimage routes, and Napoleon modeled his supply lines on their layouts. Today, engineers studying the Via Appia have found that its concrete mixture included volcanic ash, creating a self-healing material that reacts with rainwater to fill cracks. It's a haunting reminder that some of our modern infrastructure solutions are just rediscoveries of ancient wisdom. When you drive down a highway that follows an old Roman path, you're not just traveling on history, you're riding the grooves of an engineering legacy that shaped the world. Warfare in the ancient world wasn't just about brute force, it was a high-stakes chess game where engineering often decided the victor. Take the trebuchet, a medieval siege weapon so precise it could fling a 300-pound stone over 200 yards with the consistency of a modern artillery strike. Unlike earlier catapults that relied on twisted ropes for power, the trebuchet harnessed gravity itself, using a massive counterweight that swung like a pendulum. The mathematics behind it were breathtaking. Engineers calculated exact pivot points and weight distributions to maximize range, adjusting for everything from wind resistance to the moisture content of the projectile. Some designs even included slings that released at the optimal angle, turning rocks into guided missiles. What's astonishing isn't just the physics, it's that these machines were built without blueprints, using knowledge passed down through generations of trial and error. Then there's Greek fire, the Byzantine Empire's secret weapon that terrified invaders for centuries. This napalm-like substance wasn't just flammable, it clung to ships and skin, burned on water, and couldn't be extinguished by anything except sand or vinegar. The exact recipe remains lost, but historians suspect it involved distilled petroleum, pine resin, and quicklime, a mixture so volatile it was pumped through bronze tubes under pressure, creating early flamethrowers. The psychological impact was as devastating as the flames. Entire fleets retreated at the mere sight of the Byzantines' fire-bearing ships. What's remarkable is how this 7th century innovation prefigured modern chemical warfare, proving that ancient engineers understood the power of chemistry long before laboratories existed. But siege technology wasn't just about destruction, it was about problem solving under pressure. The Romans perfected the ballista, a giant crossbow powered by torsion springs made from twisted animal sinew, capable of launching arrows with enough force to impale 2 men at once. Meanwhile, the Chinese invented repeating crossbows that fired 10 bolts in 15 seconds, a feat unmatched until the invention of the machine gun. These weren't just weapons, they were feats of ergonomics and material science. The Assyrians, for example, developed mobile siege towers with adjustable ramps and water-soaked leather coverings to deflect fire arrows, essentially ancient tanks. Every innovation reflected a deep understanding of mechanics, logistics, and human psychology. Perhaps the most enduring legacy of these war machines is how their principles still echo today. The trebuchet's counterweight system inspired early concepts of potential and kinetic energy, while Greek fire's delivery mechanisms hint at modern fuel-air explosives. Even defensive innovations like the layered walls of Constantinople, designed to absorb cannon fire, influenced later fortress designs. War may have been the catalyst, but the real victory was in the minds of those who turned limitations into breakthroughs. When you see a medieval siege engine in a museum, you're not just looking at a weapon, you're seeing the birthplace of engineering itself, where necessity didn't just invent the wheel, it reinvented the future. The precision of Inca stonework isn't just impressive, it's almost supernatural. Picture a wall built without mortar, where massive stones fit together so tightly you can't slide a credit card between them, yet they've survived centuries of earthquakes that leveled modern buildings. How did they achieve this? One theory points to an almost obsessive level of craftsmanship. The Incas likely used harder stones to grind and shape each block, painstakingly adjusting them until they locked into place like a three-dimensional jigsaw puzzle. This wasn't just construction, it was a form of artistry where every angle and curve was honed by hand, often over months or even years. But here's where it gets even more fascinating. Some researchers believe the Incas might have used natural softening agents, like plant acids or fermented juices, to temporarily make the stone more malleable. Imagine applying a paste to granite that allowed it to be shaped like clay, only to harden again once the chemical reaction faded. While no direct evidence has been found, traces of organic compounds on certain stones suggest this wasn't just a wild guess. It could have been a carefully guarded secret of their stonemasons. Then there's the seismic genius behind their designs. Unlike rigid modern structures, Inca walls were built to move. The stone's irregular shapes and slightly convex surfaces allowed them to shift during earthquakes, then settle back into place like a self-healing puzzle. It's a principle modern engineers call kinetic architecture, yet the Incas mastered it 500 years ago without a single equation or computer model. Their walls weren't just strong, they were alive, dancing with the earth rather than fighting it. What's truly humbling is realizing how much knowledge has been lost. The Inca left no written records, and their techniques were passed down orally through generations of apprentices. When Spanish chroniclers asked how the stones were cut so perfectly, the answer was simple: they told the rocks where to go. To modern ears, that sounds like myth, but maybe it's a poetic truth. The Incas didn't just build structures, they listened to them, understanding stone as a partner rather than an obstacle. Today, as engineers study these walls to design earthquake-resistant buildings, we're not just learning from ancient technology, we're rediscovering a philosophy of harmony between human hands and the natural world. Among the most tantalizing mysteries of ancient engineering are the lost machines described in historical texts, devices so advanced they seem ripped from the pages of science fiction. Take Archimedes' legendary heat ray, said to have used polished bronze shields to focus sunlight and set invading Roman ships ablaze. For centuries, scholars dismissed it as myth, until an experiment in 2007 replicated the effect using mirrors, igniting a wooden boat in seconds. Was this a real weapon of war, or just a stroke of storytelling brilliance? The line blurs further with Hero of Alexandria's steam-powered Eolipile, a spinning sphere that demonstrated the principles of jet propulsion 1700 years before the Industrial Revolution. These weren't just toys, they were proof that the ancient world flirted with automation long before we credited humanity with such ingenuity. Then there's the Antiquity mechanism, a corroded bronze artifact pulled from a shipwreck in 1901 that turned out to be an astronomical computer capable of predicting eclipses and tracking planetary movements. Gears within gears, precision cut to mesh perfectly. This level of mechanical sophistication was thought impossible until at least the 1400s. How many other devices like this were lost to time? Chinese texts describe automated chariots with differential gears, while Arab engineers built programmable musical instruments powered by water clocks. These weren't isolated curiosities. They were sparks of a technological revolution that flickered brightly before being buried by war, decay, or simply the passage of centuries. What's most striking is how these inventions challenge our assumptions about progress. We imagine technology as a straight line forward, but history is full of detours and dead ends, ideas so ahead of their time they couldn't find fertile ground. Hero's steam engine could have jump-started an industrial age in the 1st century, but without a need for mass production or coal-rich economies, it remained a novelty. Similarly, the Roman glassmaker who allegedly invented unbreakable, flexible glass saw his workshop destroyed by Emperor Tiberius, who feared the material would devalue gold and silver. Innovation, it seems, has always been as much about timing as it is about genius. Perhaps the real lesson lies not in the machines themselves, but in the minds that conceived them. When archaeologists unearthed a 4,000-year-old Mesopotamian clay tablet, they found instructions for a primitive battery, a clay jar filled with vinegar and copper rods that could generate a small electric current. Was it used for electroplating jewelry or just a curiosity? We may never know, but each of these discoveries whispers the same truth. The ancient world was far more mechanically daring than our textbooks suggest. They didn't lack creativity, they lacked only the accumulated knowledge and infrastructure to sustain their leaps, and that's what makes these lost machines so haunting. They're not just relics, they're ghostly echoes of paths not taken, reminders that progress isn't inevitable, it's fragile, easily misplaced, and waiting to be rediscovered. Ancient astronomers didn't just gaze at the stars, they built machines to predict their movements with jaw-dropping precision. Take the Antiquity mechanism, a 2,000-year-old bronze device so complex it's been called the world's first analog computer. Found in a shipwreck off Greece, this intricate system of 37 interlocking gears could calculate lunar phases, eclipse timings, and even the dates of the Olympic Games. What's staggering isn't just its existence, it's the realization that this level of mechanical sophistication vanished for over a millennium before reappearing in medieval Europe. The gears were cut with such precision that modern engineers needed three-dimensional X-ray scans to fully unravel their functions. This wasn't just a tool, it was a celestial clockwork, proof that ancient Greece flirted with concepts we'd later call computer science. Meanwhile, halfway across the world, the Maya were constructing observatories like El Caracol at Chichen Itza, a tower with narrow slit windows perfectly aligned to track Venus's 18-month cycle. Why Venus? To the Maya, this planet wasn't just a dot in the sky. It was Kukulkan, a deity whose movements dictated the timing of wars and harvests. Their astronomical codices contained tables predicting solar eclipses centuries in advance, calculations so accurate they're off by mere hours compared to NASA's modern data. But here's what's truly remarkable. They achieved this without telescopes or even a written number 0, using only crossed sticks to measure angles and a base 20 counting system that turned the night sky into a mathematical canvas. These weren't isolated feats. In Cambodia, Angkor Wat's central towers align with the spring equinox sunrise, casting shadows that create a symbolic union of earth and heaven. The Nabta stone circle in Egypt, older than Stonehenge by 1,000 years, marked the summer solstice for nomadic cattle herders 6 millennia ago. What united these cultures was a shared understanding. Astronomy wasn't abstract science, it was survival. The Polynesians navigated thousands of ocean miles by memorizing star paths, while the Babylonians used planetary positions to create the zodiac, blending celestial patterns with human destiny. The genius of these systems lies in their duality. They served farmers planting crops by the Pleiades' rise, sailors steering by the North Star's fixed position, and priests interpreting eclipses as divine messages. Modern astronomers might use supercomputers, but their ancient counterparts had something equally powerful: patience. They spent generations recording data, spotting patterns we'd miss in our fast-paced world. When you stand beneath the spiral petroglyphs of Choco Canyon, tracing the 18-year cycle of lunar standstills carved into rock, you're not just seeing ancient science, you're witnessing humanity's oldest dialogue with the cosmos, written in stone and starlight. Beneath the rolling hills of Cappadocia lies a hidden world there, Enkuyu, an underground city carved 8 levels deep into volcanic rock, capable of sheltering 20,000 people for months at a time. This wasn't just a few caves connected by tunnels. It was a fully functional metropolis with ventilation shafts reaching hundreds of feet to the surface, stables for livestock, wineries, even chapels and schools, all hidden from the world above. The engineering behind it was staggering. Massive circular stone doors, each weighing up to a ton, could roll shut to seal passages in case of invasion, while narrow, twisting corridors forced attackers to advance single file, turning the city's very architecture into a defense system. What's even more remarkable is how these builders solved the problems of underground life. The ventilation shafts weren't just holes, they were carefully angled to create natural airflow, preventing stagnation while disguising the city's presence from the surface. Wells tapped into underground water sources without compromising structural stability, and communal kitchens were strategically placed near vents to dissipate smoke. This wasn't desperation, it was deliberate, sophisticated urban planning turned inward, a testament to human ingenuity under pressure. Across the Atlantic, the tunnels beneath Teotihuacan tell a different but equally fascinating story. Unlike Darinkuyu's defensive purpose, these subterranean passages lined with mica and mercury seem to have served ritual and political functions. Recent scans revealed chambers aligned with celestial events, suggesting they were part of a larger cosmological design. The presence of liquid mercury, a substance associated with portals to the underworld in Mesoamerican belief, hints at ceremonies where rulers may have symbolically traveled between realms. Here, underground engineering wasn't just practical, it was sacred, blurring the line between architecture and mythology. From the cliffside dwellings of Petra to the labyrinthine catacombs of Rome, these hidden networks reveal a universal truth. Ancient civilizations didn't just build upward, they mastered the earth itself. In Malta, the hypogeum of Hal Saflieni's echoing chambers were acoustically tuned to amplify specific frequencies, possibly for ritual soundscapes. Meanwhile, China's Longyu caves, with their precision-carved walls and pillars, defy explanation, their purpose still debated centuries later. Each of these spaces speaks to a profound understanding of geology, physics, and human need, proving that sometimes the greatest marvels aren't the ones that scrape the sky, but those that vanish beneath our feet. Ancient builders didn't just construct temples, they wove entire cosmologies into stone. Take the ziggurats of Mesopotamia, towering stepped pyramids that served as literal stairways to the gods. Each level represented a different plane of existence, from the earthly realm at the base to the divine at the summit. The great ziggurat of Ur, with its 3 massive terraces painted in symbolic colors, black for the underworld, red for the living world, white for the heavens, wasn't just a religious site. It was a 3-dimensional map of the universe, a physical manifestation of humanity's place in the cosmic order. The staircases ascending its sides weren't merely functional, they mirrored the path of the soul's journey, turning architecture into theology. Half a world away, the Maya built pyramids that doubled as celestial calendars. At Chichen Itza, during the spring and autumn equinoxes, the setting sun cast shadows along El Castillo's staircase that resemble a serpent slithering downward, an embodiment of Kukulkan, the feathered serpent god. This wasn't just an artistic flourish, it was precise astronomical engineering. The pyramid's 4 sides each have 91 steps, totaling 364 when combined with the shared platform at the top, one step for each day of the solar year. Every angle, every dimension held meaning, turning stone into a sacred almanac. Even the seemingly chaotic layouts of ancient cities often hid profound symbolism. Angkor Wat's 5 central towers mirror the 5 peaks of Mount Meru, the mythical home of Hindu gods, while its surrounding moat represents the cosmic ocean. Gothic cathedrals like Chartres encoded the golden ratio into their floor plans, with stained glass windows positioned to transform sunlight into divine illumination at specific hours. The Parthenon's subtle curvature and tapered columns weren't just aesthetic choices, they created optical illusions to make the temple appear perfectly proportioned when viewed from below, a visual metaphor for the harmony between human perception and divine perfection. What's most striking is how these symbolic designs transcended cultures and continents. The Egyptians oriented their pyramids to Orion's belt, linking pharaohs to the stars, while Native American mounds like Cahokia's Monk's Mound aligned with solstice sunrises. In India, temple gateways called gopurams depicted entire mythological scenes, turning architecture into storytelling. These weren't arbitrary decisions. They reflected a universal human impulse to embed meaning into the physical world. The genius of these ancient architects lay in their ability to make the invisible tangible. A spiral staircase in a Mesopotamian temple might represent the ascent to enlightenment, while a cathedral's rose window could encode Kabbalistic mysteries in its tracery. When we walk through these spaces today, we're not just seeing buildings, we're reading a language of stone and shadow, one that speaks of humanity's endless quest to bridge earth and sky. The next time you stand before an ancient structure, look closer. Those weathered stones might just be whispering secrets older than time itself. The vast oceans that separated ancient civilizations weren't barriers, they were highways, navigated by master shipbuilders who turned logs and reeds into transoceanic marvels. Consider the Phoenicians, whose sleek triremes dominated Mediterranean trade routes over 3,000 years ago. These weren't just boats, they were feats of hydrodynamic engineering, with tapered hulls that cut through waves like knives and 3 tiers of oarsmen generating unparalleled speed. The secret lay in their mortise and tenon joinery, interlocking wooden planks sealed with pitch and reinforced with dowels, creating vessels so watertight they rarely needed repairs even after years at sea. But what truly set them apart was their dual-purpose design. The same ships that carried olive oil and Tyrian purple dye could transform into warships with a bronze ram affixed to the prow, proving that ancient maritime engineering was as much about adaptability as it was about endurance. Meanwhile, on the other side of the world, Polynesian navigators were achieving the impossible, crossing thousands of miles of open Pacific in outrigger canoes stitched together with coconut fiber. Their secret weapon wasn't just the canoe's iconic lateral float, which stabilized the vessel in rough seas, but their mastery of materials. Breadfruit wood provided buoyancy, while pandanus sails could be adjusted to catch the slightest breeze. These builders understood ocean currents like modern commuters know subway lines, crafting vessels light enough to beach on sandy shores yet sturdy enough to withstand typhoons. The real genius, though, lay in their navigation techniques. Without compasses or charts, they memorized wave patterns, tracked bird migrations, and followed the subtle shifts in star paths, turning the night sky into a celestial GPS. What's often overlooked is how these maritime innovations fueled cultural revolutions. Phoenician ships carried not just goods but alphabets, spreading the precursor to modern writing systems from Lebanon to Spain. Polynesian double-hulled wire transported entire families with livestock and crops, enabling the settlement of islands from Hawaii to New Zealand. These weren't isolated feats. They were the internet of antiquity, connecting continents and weaving together technologies, religions, and ideas. Perhaps the most humbling realization is how much we've forgotten. Modern engineers still puzzle over the Phoenicians' Schemata, a mysterious rope tensioning system that acted like a prehistoric suspension bridge, keeping hulls rigid in storms. Similarly, the precise lashing techniques of Polynesian canoe builders, which allowed flexibility without weakness, remain unmatched by synthetic fasteners today. When we see replicas of these ancient vessels completing transoceanic voyages in the 21st century, it's not just a tribute to history, it's proof that some solutions are timeless. The next time you board a modern cruise ship, remember, its legacy begins with the hands of builders who saw the sea not as a boundary, but as a beginning. Whispers travel through Malta's Hal Saflieni hypogeum like ghostly echoes, bouncing off limestone walls carved over 5,000 years ago. In this underground labyrinth, a voice spoken softly in one chamber can be heard with eerie clarity 60 feet away, acoustic precision that rivals modern concert halls. How did Neolithic builders without decibel meters or wave equations sculpt stone to carry sound so flawlessly? The answer might lie in the very shape of the spaces they created. Chambers curve inward like seashells, their surfaces subtly textured to scatter sound waves evenly, while narrow passageways act as natural amplifiers, channeling vibrations with pinpoint accuracy. This wasn't accidental. Recent studies show the hypogeum's famous oracle room resonates at exactly 110 Hz, a frequency known to alter brain activity and induce trance-like states. Suddenly, those ancient rituals described in temple carvings take on new meaning. Architecture wasn't just housing the sacred, it was engineering it. Across the Mediterranean, the theater of Epidaurus presents another sonic marvel. Built in the 4th century BC, this open-air amphitheater seats 14,000, yet a coin dropped on its circular orchestra floor can be heard in the highest row without microphones. The secret, a combination of mathematics and material science. Each limestone seat acts like a sound filter, absorbing low-frequency crowd noise while reflecting high-frequency voices from the stage. The stepped seating forms a perfect half-circle, creating wave interference patterns that prevent echoes. Even the slope of the hillside was calculated too steep, and sound would shoot over spectators' heads. Too shallow and it would dissipate. Modern engineers have tried to replicate this with computer models, only to realize the Greeks accounted for variables we're still discovering, like how morning humidity affects vocal carry. But these weren't the only cultures harnessing sound's invisible power. In Chavindahuanca, Peru, underground ducts channel water to create roaring acoustics mimicking a jaguar's growl, a spiritual shock tactic for initiates. Meanwhile, the Maya built whispering galleries at Palenque where rulers' voices seemed to emanate from statues, blending technology with theater of the divine. What unites these sites is a shared understanding. Sound shaped human experience long before we had the science to explain why. Perhaps most astonishing is how these ancient builders turned limitations into advantages. Without electronic amplification, they manipulated geometry instead. The hypogeum's painters mixed ash with their pigments to create sound-absorbent murals, while Greek theaters used copper vessels as primitive bass resonators under stages. Every solution was a dialogue between physics and intuition, proving that the best engineering doesn't just solve problems, it senses them. When you stand in these spaces today and hear a whisper travel centuries, you're not just witnessing ancient tech. You're experiencing the moment humanity first learned to bend air itself to its will. High in the Andes, the Inca didn't just carve steps into mountains, they built stairways to agricultural abundance. Their terraces transformed steep, unstable slopes into lush, productive farms that fed millions. But these weren't simple flat platforms hacked into hillsides. Each level was a masterpiece of engineering, with stone retaining walls that acted like giant sponges, absorbing rainwater during storms and slowly releasing it during droughts. The secret lay in the layers beneath the soil: gravel for drainage, sand as a filter, and rich topsoil that never washed away. Modern agronomists studying these sites have found something astonishing. The soil in these ancient terraces is still more fertile than surrounding land after 5 centuries of abandonment, a testament to their deep understanding of erosion control and nutrient cycling. Meanwhile, in the heart of Mesoamerica, the Aztecs faced a different challenge: a city built on a lake with no farmland. Their solution: floating gardens called chinampas, artificial islands woven from reeds and anchored by willow trees. These weren't just rafts with dirt piled on top. They were self-sustaining ecosystems. Farmers dredged nutrient-rich lake muck to replenish the soil annually, while the canals between plots regulated temperature like natural air conditioning. The system was so efficient it could yield up to 7 harvests per year, outproducing modern farmland. Fish swimming in the canals provided protein and fertilized crops, creating a closed-loop system that wasted nothing. Today, urban farmers in Mexico City are reviving these techniques, proving that ancient sustainability models might hold answers for our food-insecure future. What's often overlooked is how these systems doubled as climate adaptation strategies. The Inca's terraces created microclimates. Higher levels grew frost-resistant potatoes, while lower tiers nurtured maize and quinoa. The Aztecs' chinampas never flooded during heavy rains because they rose and fell with the lake's level. These weren't just farms, they were climate-resilient food factories. Perhaps most inspiring is the social engineering behind these marvels. The Inca's terrace networks required thousands of workers coordinating through a labor tax system called mita, while Aztec chinampas were maintained by families who passed down specialized knowledge through generations. Both systems show us that agricultural innovation isn't just about technology, it's about community. When you see photos of these ancient farms, you're not looking at relics. You're seeing blueprints for how humanity might once again learn to work with nature rather than against it. Walking through the ruins of Mohenjo-Daro is like stepping into a 5,000-year-old masterclass in city planning. This ancient metropolis of the Indus Valley civilization didn't just haphazardly sprout along muddy riverbanks. It was meticulously designed with wide, straight streets laid out in perfect grids, a level of organization that wouldn't become common again until the 19th century. But the real marvel wasn't just the orderly layout, it was the infrastructure humming beneath those streets. A network of brick-lined drains ran through every neighborhood, funneling wastewater away from homes and into covered sewers, a sanitation system more advanced than those in European cities just 200 years ago. Each house connected to these drains, many featuring the world's earliest known indoor toilets, complete with wooden seats and vertical chutes that flushed waste directly into the underground channels. What's even more astonishing is how these systems reflected a profound understanding of public health. Great bath complexes, like the one at the city's heart, weren't just for ritual purification, they doubled as communal hygiene hubs, with watertight floors sealed by bitumen to prevent leaks. Meanwhile, cleverly placed wells ensured fresh water was never more than a short walk away, their cylindrical brick designs preventing contamination from the surrounding soil. This wasn't just engineering, it was epidemiology in action, a civilization that intuitively grasped the link between cleanliness and survival millennia before germ theory. Yet Mohenjo-Daro wasn't alone in its foresight. Across the ancient world, urban planners demonstrated a knack for solving problems we still grapple with today. The Romans engineered their cities with pedestrian-friendly porticos shading sidewalks, an ancient version of walkable urbanism, while the Maya built raised causeways permeable enough to drain tropical rains but sturdy enough to handle heavy foot traffic. Even the layout of these cities held purpose. Mohenjo-Daro's uniform blocks discouraged overcrowding, while Teotihuacan's Avenue of the Dead aligned with celestial events, turning daily commutes into cosmic rituals. The genius of these systems lies in their holistic approach. Unlike modern cities that often bolt on solutions after problems arise, ancient planners designed for harmony from the ground up. In Harappa, another Indus Valley city, standardized bricks created modular construction, speeding up repairs without sacrificing quality. Carthage's circular harbor allowed hundreds of ships to dock simultaneously without congestion, its concentric design inspiring modern roundabouts. These weren't just conveniences, they were evidence of societies that viewed urban living as a collective responsibility rather than an individual burden. Perhaps most humbling is realizing how much we've overlooked. Modern archaeologists studying Mohenjo-Daro's sewer covers found grooves designed to let workers lift them without tools, an ergonomic detail many contemporary manhole designs still lack. The city's baked brick walls absorbed heat during the day and released it at night, naturally regulating indoor temperatures long before the invention of insulation. When we label these achievements primitive, we're not just underestimating ancient ingenuity, we're missing blueprints for sustainable living that could inspire solutions to today's urban crises. The next time you're stuck in traffic or dodging potholes, remember, 5 millennia ago, someone already had a better idea. We just forgot to take notes. Ancient civilizations didn't just rely on muscle power, they engineered ways to multiply it. Picture a team of oxen straining against a wooden yoke, their combined strength channeled through a simple but revolutionary device, the plow. This wasn't just farming equipment, it was one of humanity's earliest mechanical advantage systems. By distributing the animal's pulling force across a wide blade, a single operator could till fields that would have taken dozens of workers with hand tools. The genius lay in the details: curved wooden yokes that fit the oxen's shoulders comfortably, iron tips that reduced soil resistance, and adjustable angles to control depth. What seemed like basic technology was actually biomechanical optimization, allowing societies to feed growing populations with fewer laborers. But animals weren't just for agriculture, they became living cranes on construction sites. The Romans perfected this with their treadwheel crane, a marvel where donkeys or slaves walked inside a giant wooden wheel, turning it like a hamster wheel to hoist multi-ton stone blocks. One surviving example in the Roman port of Ostia could lift over 6,000 pounds, equivalent to a small car, using nothing but coordinated foot power. The secret was in the gearing. Ropes wound around a drum as the wheel turned, with each rotation providing incremental lifting power. This wasn't brute force, it was physics harnessed through clever design. Even more impressive were the adaptations across cultures. In China, square pallet chain pumps used oxen to rotate water wheels, lifting water from rivers to irrigate terraced fields. The Egyptians employed teams of laborers to drag sledges up ramps, but with a twist they poured water ahead of the sledges to reduce friction, effectively creating a primitive lubricant. Every innovation shared a common thread, maximizing output while minimizing strain. What's often overlooked is how these systems reflected deep observation of animal behavior. The yoke's design evolved to avoid restricting oxen's breathing, while harnesses for horses shifted pressure to their chests rather than throats after cultures realized throat-based harnesses could suffocate them. This intersection of zoology and engineering hints at something profound. Ancient innovators didn't just use animals as tools. They partnered with them, adapting technology to biology in ways that benefited both species. Perhaps the most enduring legacy of these systems is their simplicity. Unlike modern machinery reliant on fossil fuels, animal-powered devices were sustainable, repairable with local materials, and adaptable to varying conditions. When you see a medieval drawing of a horse turning a millstone or a Persian qanat worker guiding a donkey-loaded bucket of earth, you're not just looking at old tools. You're seeing the roots of mechanical thinking the moment humanity realized that with the right leverage, even the smallest force could move mountains. Ancient builders didn't just construct shelters, they conducted a silent dialogue with the elements, shaping stone and clay into climate-responsive masterpieces. In the scorching deserts of Persia, where summer temperatures could melt lead, engineers devised wind catchers, towering chimney-like structures that captured even the faintest breeze and funneled it downward into homes. But these weren't just passive air ducts. The interior shafts often passed over underground qanat waterways, chilling the air through evaporation before it entered living spaces. Some designs even included wet reed mats at the intake, transforming dry desert winds into cool drafts. The result, natural air conditioning that dropped indoor temperatures by up to 20 degrees without a single watt of electricity. Meanwhile, high in the Andes, where nights could freeze even in summer, Inca architects worked with the opposite challenge. Their solution lay in thick adobe walls, not just any mud bricks, but mixtures carefully calibrated with straw for insulation and animal hair for tensile strength. These walls absorbed daytime heat like thermal batteries, slowly releasing it after sunset. Double-thatched roofs provided dead air space to trap warmth, while trapezoidal doorways, wider at the base, prevented heat loss through convection. Every design choice served a dual purpose. The same massive walls that conserved heat also withstood earthquakes, proving that climate adaptation and structural resilience often went hand in hand. Coastal civilizations faced their own trials. In the cyclone-prone regions of ancient India, builders of the Harappan civilization elevated homes on mud brick platforms, allowing floodwaters to pass underneath without destroying dwellings. The Maya took a different approach in their rainforest cities, designing steeply pitched roofs with wide eaves that shed torrential rains while creating shaded verandas for ventilation. Even the orientation of buildings held meaning. Mesoamerican palaces often aligned with prevailing winds to create natural cross breezes, while Egyptian homes positioned windows to exploit the Nile's cooling evening air currents. What's striking is how these ancient principles are resurfacing in modern sustainable architecture. Contemporary engineers studying Persian wind catchers have adapted their designs for solar chimneys in eco-homes, while Adobe's thermal mass properties inspire energy-efficient buildings from New Mexico to Australia. The bunga huts of Gujarat's desert, with their circular shapes minimizing surface area exposed to heat, now inform low-energy housing projects in hot climates. Perhaps the most profound lesson isn't just in the techniques themselves, but in the mindset behind them. These builders didn't conquer their environments, they listened to them, turning constraints into innovations. As climate change reshapes our world, these ancient strategies take on new urgency. The floating villages of Southeast Asia, built on flexible bamboo frames that rise with floodwaters, offer models for flood-prone regions. The subterranean dwellings of Cappadocia, maintaining constant temperatures year-round, inspired geothermal heating solutions. Even something as simple as the whitewashed walls of Mediterranean villages reflecting sunlight to reduce cooling needs is being rediscovered as a low-tech answer to urban heat islands. The genius of these ancient systems lies in their holistic view. They didn't just solve isolated problems, they created interconnected systems where architecture, climate, and daily life flowed together seamlessly. When a Bedouin tent's black fabric absorbs winter sun by day and radiates heat by night, or when a Tibetan monastery's tram wall stores solar energy in dark stone, we're witnessing more than clever engineering. We're seeing a philosophy that modern sustainability is only beginning to relearn. The most effective designs don't fight nature, they speak its language. Even the greatest builders of antiquity faced setbacks, monuments that leaned, towers that crumbled, and bridges that collapsed under their own ambition. Take the Leaning Tower of Pisa, that iconic slanting bell tower that's become a global symbol of unintended architectural quirkiness. What few realize is that its famous tilt wasn't some artistic choice, it was a glaring engineering miscalculation. The builders laid its foundation on soft, unstable clay soil just 3 meters deep, and by the time they reached the third story, the entire structure was already sagging to one side. Rather than abandon the project, they tried compensating by making upper floors slightly taller on the sinking side, a desperate fix that only exaggerated the lean over centuries. Today, engineers study Pisa's tilt as a masterclass in soil mechanics, proving even medieval builders underestimated the invisible forces beneath their feet. Then there's the tragic fate of the Lighthouse of Alexandria, one of the ancient world's 7 wonders. Standing over 300 feet tall, its gleaming mirror could supposedly reflect sunlight to burn enemy ships, though modern scholars debate whether that was myth or reality. What we know for certain is how it fell, not to invasion or neglect, but to a series of earthquakes that exposed a fatal flaw in its design. The lighthouse's upper sections, built from lighter materials to reduce weight, couldn't withstand the tremors that left its heavy granite base intact. This stark lesson in load distribution echoes in modern skyscrapers, where engineers carefully balance weight versus flexibility to resist seismic shocks. But failures weren't just about physics, they revealed cultural blind spots too. The Roman Emperor Nero's Domus Aurea, a sprawling palace with a revolving dining room powered by slaves, collapsed because its extravagant design outpaced material science. The concrete used for its innovative dome hadn't fully cured when decorations were added, causing cracks that spread like spider webs. Similarly, China's pagoda of Fogong Temple survived nearly 1,000 years not because of its wooden frame, but despite it. Builders later realized its interlocking brackets only worked because each generation repaired rot before it spread, a maintenance lesson modern architects often ignore in favor of set-and-forget designs. What makes these ancient failures so valuable is how they mirror modern engineering dilemmas. When the Maya city of Capon's grand staircase collapsed due to an unstable foundation, it wasn't so different from contemporary buildings sinking into reclaimed land. The difference: ancient builders lacked standardized testing, relying instead on observation and adaptation. The Mesopotamians, for example, learned to mix straw into their mud bricks after watching untempered walls crumble in rains, an empirical approach that predated material science by millennia. Perhaps the most profound lesson lies in how these civilizations responded to disaster. After the Hanging Gardens of Babylon's irrigation system failed, likely due to sediment clogging its screw pumps, later engineers developed self-cleaning silt traps. When Greek theaters like the one in Ephesus suffered acoustical failures from misplaced reflective surfaces, builders adjusted angles until whispers carried to the back rows. Each catastrophe became a stepping stone, proving innovation isn't just about triumph, it's about learning where the cracks begin. these so-called mistakes were really prototypes in disguise, trial runs etched in stone rather than computer models. Today's engineers still reference the collapse of Rome's Mulvian Bridge when designing flood-resistant spans, or study the subsidence of Mayan reservoirs to improve modern water storage. The irony is striking. We've advanced from copper tools to carbon fiber, yet we're still deciphering the same lessons ancient builders scrawled in rubble. Their failures weren't dead ends, they were the first drafts of progress, written in a language of crumbling mortar and stubborn human resolve. Beneath the gleaming marble of the Parthenon and the towering stones of the pyramids lies a truth as old as civilization itself. These marvels were often raised by hands that had no choice. The same societies that calculated the golden ratio and charted the stars also relied on systems of forced labor that shaped their grandest achievements. Take Rome's Colosseum, where enslaved laborers quarried travertine blocks under whips and scorching sun, or the Great Wall of China, where conscripted workers' bones were said to be mixed into the mortar. This duality isn't a footnote, it's central to understanding how these wonders came to be. The precision of Egyptian obelisks, the symmetry of Mayan temples, these weren't just triumphs of engineering, but of coerced human endurance. Yet reducing these projects to mere exploitation misses the nuance. Some ancient builders, like the Inca, used a rotational labor system called mita, where communities contributed work as a form of tax. While still demanding, it functioned within a reciprocal social contract, with workers compensated through feasts and access to state resources. Similarly, Roman enslaved architects like Vitruvius could sometimes earn freedom through their skills, proving that forced labor existed on a spectrum, from brutal chains to complex systems of obligation. The Assyrians took a different approach, deporting entire skilled populations after conquests, turning artisans into a permanent underclass that built Nineveh's splendors. What's often overlooked is how slavery itself drove innovation. The Roman ergastulum, a prison-like barracks for enslaved laborers, was strategically placed near construction sites to minimize transport time, a grim precursor to modern project management. Pharaohs organized work crews into competing teams, using rivalry to boost productivity at Giza, while Mesopotamian overseers developed early accounting methods to track brick quotas. These weren't just moral failures, they were calculated systems that treated human lives as variables in engineering equations. The ethical weight of this history lingers in the stones. When we admire Petra's rose-colored facades, we're also seeing the shadows of Nabatean slaves who dangled from ropes to carve them. The perfect joints of Machu Picchu's walls whisper of laborers who shaped granite with nothing but stone tools and relentless toil. Acknowledging this doesn't diminish the architectural genius, it deepens our understanding of how civilizations balanced brilliance and brutality. These monuments weren't just built with pulleys and levers, they were forged from the tension between human ingenuity and human suffering. Perhaps the most haunting lesson lies in how these societies justified such systems. Greek philosophers like Aristotle argued slavery was natural, while Egyptian texts portrayed forced labor as service to the gods. These weren't just excuses, they were cultural frameworks that allowed progress and oppression to coexist. Today, as we trace the fingerprints left in ancient mortar, we're reminded that engineering is never purely technical, it's a mirror reflecting who we are, for better and worse. The true legacy of these wonders isn't just how they were built, but the uncomfortable questions they force us to ask about what we're willing to sacrifice in the name of greatness. History often paints ancient engineering as a male-dominated field, but scratch beneath the surface, and you'll find women shaping the built world in ways we're only beginning to recognize. Take Enheduanna, the Akkadian high priestess of Mesopotamia in the 23rd century BCE. More than just a poet and religious leader, she oversaw the construction of temples and ziggurats, coordinating teams of laborers and artisans with the precision of a modern project manager. Her hymns weren't mere prayers, they were blueprints for sacred spaces, blending spiritual vision with architectural logistics. When she wrote of the true measuring rod and the measuring line, she wasn't just speaking metaphorically. She was documenting the tools that transformed celestial alignments into stone and mortar. Then there's Pharaoh Hatshepsut, whose mortuary temple at Deir el-Bahari stands as one of Egypt's most audacious engineering feats. While her reign is often remembered for its political drama, her architectural legacy reveals a mastermind at work. The temple's terrace design, cut into limestone cliffs, required complex retaining walls and hidden drainage systems to withstand flash floods, solutions that still baffle engineers today. What's more, her expeditions to Punt brought back not just exotic goods but construction innovations, like the use of tamarind resin as a waterproofing agent. This wasn't just a ruler commissioning buildings. This was a woman deeply involved in the technicalities of engineering, challenging the notion that ancient women were confined to the sidelines. But these famous figures are just the tip of the chisel. In Minoan, Crete, frescoes depict women overseeing the construction of elaborate drainage systems, their roles evident in the detailed records of material shipments and workforce management. The Roman architect Vitruvius casually mentions a female colleague, Phyle, who designed harbors and siege engines, her contributions preserved only in passing references. Even in cultures with strict gender roles, exceptions emerged like the anonymous female potters of the Indus Valley, whose standardized weights and brick ratios suggest they played key roles in urban planning. What's heartbreaking is how easily these stories were erased. Many ancient female engineers likely worked anonymously, their achievements attributed to husbands or male patrons. The Babylonian queen Semiramis, for instance, was said to have built the legendary Hanging Gardens, but later historians dismissed her as a myth. Recent archaeology tells a different story. Cuneiform tablets reveal women managing vast construction budgets, their names stamped on contracts for canal repairs and bridge projects. Uncovering these narratives does more than correct historical biases, it reshapes our understanding of innovation itself. When we examine the woven suspension bridges of the Andes, maintained for centuries by Quechua women's collectives, or the female-led guilds that crafted Gothic cathedrals' stained glass, we see engineering as a collaborative human endeavor, not a gendered one. The next time you marvel at an ancient wonder, ask yourself, whose hands truly shaped it? The answer might just rewrite history. Ancient myths weren't just campfire stories. They were encrypted archives of engineering knowledge, blending fact and metaphor to preserve techniques too valuable to lose. Take the bronze giant Tolos from Greek mythology, a towering automaton said to patrol Crete's shores. While it's easy to dismiss this as pure fantasy, consider the details. Joints sealed with molten lead, a single vein of life-giving fluid running from neck to ankle. These aren't arbitrary features, they're startlingly accurate descriptions of primitive hydraulic systems. Archaeologists have found evidence that Greek craftsmen actually built small mechanical statues with fluid-powered movements, using techniques later perfected in Alexandria's famed automata. The myth of Tolos might well be the ancient equivalent of an engineering schematic wrapped in narrative. Meanwhile, Sanskrit texts describe Vimana's flying chariots with elaborate propulsion systems, complete with references to mercury vortex engines and protective wind-resistant shells. For centuries, these passages were considered purely allegorical until researchers noticed parallels between their descriptions and modern aerospace principles. The so-called mercury vortex bears eerie resemblance to ion propulsion concepts, while the emphasis on aerodynamic shapes mirrors contemporary aircraft design. Whether these were observations of actual technology or astonishingly prescient speculation remains hotly debated, but one thing is clear: someone was thinking rigorously about flight mechanics long before the Wright brothers. Even the Bible's account of Solomon's temple contains construction details so precise they've guided modern reconstruction attempts. The description of Molten Sea, a giant bronze basin supported by 12 oxen statues, matches foundry techniques from Phoenician metal workshops. The mention of windows with narrowed frames likely refers to an early form of load distribution, where tapered openings strengthened walls against lateral forces. These weren't just poetic flourishes, they were technical manuals disguised as scripture, ensuring survival through oral tradition when written records could be lost. What's fascinating is how universally this pattern appears. Norse legends speak of magical forges that never cool, a possible reference to early blast furnaces discovered in Viking settlements. Chinese myths describe Emperor Yu controlling floods with self-moving, dredging tools that archaeologists now believe were primitive trenchers powered by water wheels. The Aboriginal story of the rainbow snake creating riverbeds aligns with recent geological findings about ancient water management systems in Australia's arid interior. Everywhere we look, the line between myth and engineering blurs. The brilliance of this encoded knowledge lies in its dual purpose. By embedding techniques in memorable stories, ancient cultures ensured their preservation across generations. A blacksmith might forget a metallurgy formula, but he'd remember the tale of Hephaestus crafting Zeus's thunderbolts complete with details about quenching metals in special waters. These narratives became living textbooks, their layers of meaning accessible to both laypeople and initiates. When medieval alchemists spoke of the green lion devouring the sun, they weren't just being cryptic, they were preserving chemical processes for extracting gold from alloy using plant acids. Today, researchers are decoding these mythic blueprints with fresh eyes. The Maori story of Maui slowing the sun might encode celestial navigation techniques, while Aztec accounts of floating gardens perfectly describe their Chinampa farming systems. Even King Arthur's sword Excalibur, said to be forged in Avalon, could reflect advanced Celtic steel-making methods lost during the Dark Ages. The more we examine these stories, the more we realize our ancestors weren't just making up tales. They were writing the first drafts of engineering history, wrapping truth in wonder so it would never be forgotten. Modern engineers are turning to the past not out of nostalgia, but necessity, discovering that ancient solutions often outshine cutting-edge technology. Take Roman concrete, that mysterious blend of volcanic ash and seawater that's lasted millennia while modern counterparts crumble in decades. When scientists finally cracked its chemical code, they found something revolutionary. The seawater reacting with the ash forms rare minerals that actually heal cracks over time. Laboratories are now racing to replicate this self-repairing property, blending industrial byproducts like fly ash to create eco-friendly concrete that could slash global carbon emissions from construction. It's a paradox. The future of sustainable building might lie in a recipe perfected before the fall of Rome. Meanwhile, seismic engineers are scrutinizing Inca stonework for lessons in survival. In Peru, where earthquakes regularly topple modern buildings, 500-year-old Inca walls stand unshaken. Their secret, stones shaped like three-dimensional puzzle pieces that dissipate seismic energy through controlled movement. Japanese architects have adapted this principle in Tokyo's skyscrapers, replacing rigid steel frames with flexible joints inspired by those ancient masonry techniques. The same logic applies in California, where retrofitted buildings now incorporate rocking cores that mimic how Inca stones sway then settle back into place. Even forgotten agricultural wisdom is resurfacing in climate crises. The desert farming techniques of the Nabateans, who cultivated arid lands using intricate terracing and microcatchments, are being revived in Australia's outback to combat drought. Their underground cisterns, lined with waterproof plaster, lost less water to evaporation than modern reservoirs. Similarly, the Maya's milpa system, which intercropped corn with nitrogen-fixing beans and squash, is inspiring regenerative farms from Mexico to Kenya as a sustainable alternative to monoculture. What unites these rediscoveries is a shift in perspective. Where earlier generations saw primitiveness, we're now recognizing sophistication. The passive cooling of Persian wind catchers informs zero-energy skyscrapers in Dubai, while the hydraulic engineering of Angkor Wat's reservoirs helps Cambodian farmers adapt to erratic monsoons. Perhaps the most humbling lesson isn't just that ancient solutions work, it's that many were inherently sustainable, designed for longevity in a world without cheap energy or disposable materials. The real breakthrough isn't merely borrowing old techniques, but understanding the thinking behind them. When Venetian engineers study how the Romans used pozzolana to protect harbor structures from saltwater corrosion, or when aerospace researchers examine Egyptian linen-based glues for lightweight composites, they're not just copying, they're collaborating across centuries with minds who saw problems differently. In an age of climate change and resource scarcity, these time-tested innovations offer something priceless, proof that human ingenuity, when aligned with nature's logic, can build wonders that endure. The Parthenon's crumbling marble columns stand as more than just ancient ruins. They're the epicenter of a fiery modern debate. Should we restore them to their original glory using the same tools and techniques that built them, or freeze time, leaving every crack and stain as a testament to history? This isn't just about mortar and stone, it's a clash of philosophies. On one side, traditionalists argue that using ancient methods like the original iron clamps sealed with molten lead honors the builder's intent. When Greece restored the Erechteans caryatids, they employed Pentelic marble from the same quarries used 2,000 years ago, even replicating the subtle curvature that tricks the eye into seeing perfection. But critics warn this risks becoming historical cosplay, erasing the visible layers of time that make these structures living documents. The controversy grows thornier when artifacts are far from home. The Elgin marbles, ripped from the Parthenon's frieze in the early 1800s and now displayed in London's British Museum, have become a lightning rod for repatriation battles. Greece insists they're stolen heritage, while the museum claims they're universal cultural property, preserved from Ottoman neglect. Meanwhile, digital scanning offers a provocative middle ground. Companies like Iconom create millimeter-perfect 3D models, allowing virtual reunification of scattered fragments without moving a single stone. But can pixels ever replace the aura of standing before the real thing? Ethical dilemmas multiply with reconstruction projects. When China rebuilt sections of the Great Wall using modern concrete, purists decried it as a historical fake, while locals welcomed the tourism boom. In Warsaw, the painstaking post-war reconstruction of the old town using 18th century paintings as blueprints raised haunting questions. Is it still the same city, or a carefully crafted replica? The answer may lie in intent. Japan's Ai's Grand Shrine has been ceremonially rebuilt every 20 years since the 7th century, not as restoration but as renewal, a spiritual practice where the act of rebuilding is as sacred as the structure itself. Perhaps the most poignant tension lies in what we choose to preserve. When ISIS bulldozed Palmyra's temples, archaeologists faced an impossible choice: recreate the lost monuments from old photographs, or leave the rubble as a memorial to barbarity. Some argue intervention dishonors the past's authenticity. Others counter that neglect is its own form of violence. The Bamiyan Buddhas, dynamited by the Taliban in 2001, now exist as ghostly projections, laser beams tracing their absent forms in the Afghan cliffs. Is this preservation or performance art? Underneath these debates simmers a deeper question. Who gets to decide, descendant communities, academic experts, or the global public? When Native American tribes demand reburial of ancestral remains held in museums, or when Egypt insists the Rosetta Stone belongs in Cairo, these aren't just custody battles, they're reckonings with colonialism's legacy. Technology tantalizes with compromises, blockchain ledgers tracking artifact provenance, or augmented reality letting visitors see missing pieces in situ. But no innovation can resolve the core dilemma whether history is a relic to be protected or a story to be retold. The irony is that ancient builders themselves would likely find these debates baffling. The Romans routinely recycled marble from older structures, while medieval churches built atop pagan temples saw no contradiction. Perhaps the wisest approach comes from Venice's caretakers, who have maintained the city's foundations for 1,000 years with a simple philosophy. We don't preserve Venice as it was, we preserve it so it can keep becoming. In the end, these structures were never meant to be frozen in time. They were built to live, change, and spark conversation across centuries. The real challenge isn't choosing between past and present, it's learning to listen to both. The jungles of Cambodia hide more than vines and wildlife beneath the dense canopy. Lasers are mapping the bones of a civilization we barely knew existed. LiDAR technology, which uses pulsed light to penetrate vegetation, has revealed sprawling urban networks around Angkor Wat, complete with highways, reservoirs, and neighborhoods that rewrite our understanding of the Khmer Empire. This isn't just filling in gaps, it's uncovering entire chapters of human achievement. In the Amazon, similar scans exposed geometric earthworks spanning hundreds of miles, proof that what Europeans dismissed as an untouched wilderness was actually a carefully engineered landscape. These discoveries aren't merely adding dots to the map, they're connecting them into patterns that show how ancient cultures transformed their environments on scales we're only beginning to comprehend. Meanwhile, inside the Great Pyramid, muon tomography, a technique that uses cosmic rays to peer through stone, has detected hidden chambers and passageways that evade traditional exploration. Robots equipped with fiber optic cameras have navigated shafts no human could enter, uncovering markings left by builders 4,000 years ago. In Rome, ground-penetrating radar has mapped Nero's long-lost Golden House beneath modern streets, revealing frescoed halls buried by later emperors trying to erase his legacy. These tools do more than reveal hidden spaces. They let us witness the creative process of ancient engineers, from the initial chisel marks to the adjustments made mid-construction when plans changed. What's truly revolutionary is how these technologies democratize discovery. Where once only wealthy institutions could fund excavations, now drones and photogrammetry allow local researchers to create precise 3D models of sites from a handful of smartphone photos. In Syria, where war has destroyed priceless heritage, archaeologists used pre-conflict satellite imagery and crowdsourced photos to digitally reconstruct the Temple of Bel before ISIS obliterated it. These digital twins aren't just backups, they're interactive classrooms where students worldwide can walk through ancient streets, measuring doorways and testing acoustics as if they'd stepped through time. Yet the most exciting breakthroughs may lie in the data we've already collected but haven't fully understood. Machine learning algorithms are sifting through decades of excavation reports, spotting patterns no human could, like how Inca stonemasons consistently oriented certain joints to withstand seismic waves, or why Roman concrete samples from different regions show subtle variations in durability. These aren't just academic exercises, they're yielding practical insights. Modern engineers studying the self-cooling properties of Yemen's ancient mud skyscrapers, mapped in exquisite detail by laser scans, are adapting their passive ventilation techniques for energy-efficient buildings in Dubai. The future of ancient engineering isn't just about looking back, it's about collaborating across centuries. When a team in Peru used LiDAR to rediscover thousands of forgotten terraces, they partnered with local farmers to revive these prehistoric agricultural techniques, boosting crop yields in drought-stricken regions. In Turkey, 3D printed replicas of Hittite water systems are helping villagers restore ancient irrigation channels abandoned for generations. This fusion of cutting-edge tech and ancestral knowledge hints at a new paradigm, one where the past isn't a relic but a living toolkit for solving today's crises. As these tools grow more sophisticated, they're challenging our assumptions about antiquity's limitations. Recent spectral imaging of the Antikythera mechanism revealed hidden inscriptions, a user manual etched in bronze, suggesting such devices were more common than we thought. Underwater drones exploring Mediterranean shipwrecks keep finding intricate gears and precision tools that hint at widespread mechanical sophistication. Every scan, every pixel whispers the same truth. We've underestimated our ancestors. Their primitive world may have been a web of innovation we're only now learning to see. The real revelation isn't just what they built, but how much they knew and how urgently we need to listen. The towering pyramids, the whispering acoustics of ancient theaters, the earthquake-defying walls of Machu Picchu, these aren't just relics of a bygone era. They're masterclasses in problem-solving, left behind by civilizations who refused to accept the limits of their time. What's astonishing isn't just what they built, but how their breakthroughs echo in our modern world. The Roman concrete that heals itself, the Inca masonry that dances with tectonic plates, the Persian wind catchers that cooled cities without electricity, these weren't just clever tricks. They were revolutions born from observing the natural world with a clarity we're only now relearning. But here's the real magic. These ancient secrets aren't locked away in textbooks or buried under dust. They're alive, reshaping how we tackle today's greatest challenges. Engineers studying the self-cooling properties of Yemen's mud skyscrapers are reinventing sustainable architecture. Urban planners are reviving the Indus Valley's flood-resistant designs as climate change redraws coastlines. Even NASA has looked to the Maya's drought-proof reservoirs for inspiration in designing closed-loop life support systems for Mars. The past isn't just a curiosity, it's a collaborator, offering blueprints we didn't know we needed. Yet for all we've uncovered, so much remains tantalizingly out of reach. The Antikythera mechanism hints at mechanical sophistication we never attributed to ancient Greece. The precision of Puma Punku's stonework defies explanation. It's cut so precise they seem laser-made. And who's to say what other marvels lie buried, waiting for the next generation of explorers to reveal them? Every time a new technology peels back another layer, LiDAR revealing lost cities, muon tomography unmasking hidden chambers, we're reminded how much history still has to teach us. This isn't about romanticizing the past or dismissing modern innovation. It's about recognizing that brilliance isn't bound by era. The same human ingenuity that charted the stars without telescopes, that moved mountains without machinery, still pulses in us today. The difference: we stand on the shoulders of those ancient giants, able to see further because they showed us how. So the next time you walk past a skyscraper or cross a bridge, take a moment to listen. Somewhere in its design, in its materials, in its very soul, you might just hear the whisper of a forgotten builder still guiding us forward. Now it's your turn. Which ancient wonder leaves you awestruck? Is it the impossible precision of the Great Pyramid or the haunting beauty of Petra's rose-colored facades? Drop your pick in the comments and let's keep the conversation going. And if you've enjoyed this journey through history's hidden genius, hit that subscribe button because the past has plenty more surprises in store, and we're just getting started.